Well, here we are. Started a little bit early, well, like a minute early, just to kind of see, because last time I streamed, we had problems with the delay and all that, and it looks like we might have that problem again, but I don't know. So I just started like a minute early just to try it out, and we'll see what happens. So it looks like we may or may not be having trouble. Says I got yellow, which is okay, I suppose. I'm going to stop it and start it again, but we're almost time to start, so we need to, we're going to get going here. I'm just going to see something, so let's see. See something, then we could say something. So, hello. So, that's that. Oh, it looks like I'm pretty good, but I might only be talking to myself. I don't know. But it is 7 o'clock. And I'm going to actually start recording now. Unfortunately, with the live stream, it's going to catch that little intro. Apologize. Just, skip to the good stuff if you want. You'll know. Hey, Becca. I don't know if I know you, but hi. All right. I'm going to start the recording. And so we have our physics test tomorrow in my class. And so I'm just going to like usual. Hey, Aiden. What's up? Like usual, I'm going to go through kind of like the unit, just the different parts to it, and hey, Mia. And then, of course, ask me questions as you have them. So I will go slow. If the delay is off a little bit, then we'll say, hello, Caitlin. And so we'll just start right into it. So I got a question up. Which of these is the greatest rate of power? Pushing a box with 15 newtons for Lexi. What's up? Hi. Or is that, I can't tell, those are L's. Tess, what's up? Hi, Tess. Ariadna, how you doing? All right, cool. You're getting a full house here. You guys are good. Jumping in right when we're starting. So, take a look at this one, and I'm going to check the health while you guys are doing this, and it looks like we're pretty good on the delay this time, so I'm not going to be too worried yet. So, obviously this one's going to deal with some calculations, and I'm going to keep these calculation ones to a minimum because they're a little harder to do and not as much. I don't know. I feel like calculations are something that you just have to have practice with, and we've definitely done some practices with this stuff. So, yeah. So it wants to know power, and I'm just going to, before I give you the answer, we're going to just talk about power. So power is literally just work divided by the time. So obviously these all have a time, and these doesn't say anything about work though. So you're going to have to figure out work, and work, going back to the very beginning, is just going to be the force times displacement. All right, so really quick, and I realize I'm not 100% prepared. Let me get my calculator. Come here, calculator. All right, so hello, I don't know you, but welcome, and hopefully this is helpful to everybody here. Awesome, I'm glad you guys are here. All right, Noel and Sam, I'm awesome. Welcome. All right, I'm glad you didn't forget. Yes. So the thing is, what we got to do, for example, for question number 1 is, you guys, hey Jacob, what's up? So obviously, just start thinking. I'm going to get this. It seems like I'm going a little red with my sound. Is you have to figure out the work and then the power for each one. So this is going to be So for this one, this is going to be the force. This is going to be the displacement. So force and displacement, this will be the force here, and this will be the displacement, force, displacement, and so on. So basically you have to very quickly, well, it just says holding, so there's nothing about displacement there. So you have to kind of quickly do these, and so I'm just going to write the force, nope, that's going to be not what I want to do. Let's erase that. So, all right, we got A. We got choice already made. Awesome. So for 15 times 15, the 15 is going to be times 15. I'm going to get, for this one, I'm not going to do this for all of these options, but the work here is 15 times 15, 225 joules. And then if I take that and divide it by the 5 seconds, yeah, I know. I want to get started on time. You guys are amazing for popping in right at the beginning. But like with everything, I want to start on time so we could end as quickly as we can and still get some use out of this. So you remember the unit for for power is watts. So this is going to be for letter A, okay? So just to kind of recap, I figured out the work. 15 times 15 gives me 225. Divided by 5 gives me 45. So if I do that for all of them, the power, and I figure out the power, and I figure out the power. So for letter B, I'm going to take 20 divided by 10, or I'm sorry, 20 times 10, divide that by the 10 seconds, and I'm only going to get 20, so that's kind of a loser there. That's not going to be it. And let's see, if I realize there's a little pattern adjourned made to make this quicker, 30 times 5 divided by 5 is just going to leave me with 30 watts. And then finally, there's no displacement for this one, so that's going to make this power is going to be 0 divided by 20, which means the power is going to be 0. So you guys were correct. It is A. Nice job, you guys who chose it. Becca, you got a triple points. Nice job. All right, I'll mark that down somewhere. All right, that's how you do it. So to recap, because I went through it really kind of quickly here. Once I got rolling, I had to figure out the work first, okay, and then I had to figure out the power second. All right, so that's how you do those. Okay, nice and simple, right? Let me know if you got questions. I will answer them. Of course, that's the whole point of this. All right, so, but I have questions for you too, of course. And we got a kid standing on top of a 19-meter hill, has 10,536 joules of potential energy. How much work did he do to get to the top of the hill? Drink my water while I wait. Don't overthink this. Is the delay that bad? I hope not. So wants to know how much work did he do? Now we got some B's. We got some choices being made. Looks like B is the winner. Stephanie getting all fancy typing in the answer. Great. Nice. Well, yes, very good. Yeah, because work, there's two equations for work. One was the one we just saw, and the other one is work is equal to the change in energy. So because it literally tells you he has this much potential energy, that means that that's how much work he had to do to get there. So hang on, control, forget what I just circled. That is not the correct answer. That's the one, okay? So A is obviously the one that you would choose if you somehow plugged it into equations and somehow, just kind of blindly plugged into equations. But if you think about it, how much work did he do? How much energy does he have? That's how you know how much work he did, all right? So the other questions are worded in order to make you think, well, sometimes it is 0, but that's not, why is it not C? Because, see, I was just about to answer that, so you read my mind, and actually you thought of it before I started because of the delay. So work is because you're thinking of work is force times displacement, and if he's just standing still, that's how much work he's currently doing, okay? But it says how much work did he do in the past to get up to the top of the hill. So if we were to figure it out, how much work he did, there would be a displacement because he had to climb the hill. All right. So currently he's not doing any work, but he did do work to get up there. Phenomenal question, Jose. Nice job. All right. So moving on, let me know if there's questions. Okay, I'm gonna keep it rolling just like usual, but pop in with questions. I'll go back if I need to. I'm not sure what kind of delay we're getting. So, all right, which of the following are true about energy? So it could be more than one. Actually, it kind of hinted that there is more than one. So look at them. Tell me which ones are true. All right, more than one. Let's see. A is one of the correct answers. Good. That is basically the definition of energy. It's the ability to do work. So that is true. F is also true. Good. That is true. It can be stored. That's the whole idea of potential energy. Okay. Good. A, yep. Yep. G is true. It could change forms. Yes, it can definitely change forms. You go from potential to kinetic and back again. G, but not D. Okay, G, yes. A, G, F, good, good. Yes, those are all good. C, it can cause an acceleration. Yes, it definitely can cause an acceleration. All but D. Well, that's a very nice answer. Let's see if these are true. It can slow something down. Can it slow something down? Well, yeah. And that's what we call negative work, or work that takes away energy. So yes, it can definitely slow something down. E and F, yes, true. Good, good, yes. And then it can result in a constant speed. That's kind of tricky, but if you think about it, it's just energy. Yeah, I mean, it doesn't say anything about having to, change it to speed. It can result in a constant speed because if you're doing work, you could be pushing something and you're doing work on it if it's moving. So yeah, it's all but D, okay? And sometimes you'll see that word. That doesn't mean it's always, when you see the word always, that doesn't mean it's definitely false, okay? That's just a yellow flag. You wanna check it, okay? But in this case, yeah, it doesn't always cause an acceleration, because look at letter E. It could cause just a constant speed. It doesn't have to cause an acceleration. So yeah, all of them are true except for D. All right, nice job. Yep, Sam got it. Okay. Now, I kind of pre-chewed the math for you here, but I pre-chewed it in different ways. And so we got a 500 Newton box, push up a ramp. The ramp is 3 meters long, right? So in other words, from here to here is 3 meters, okay? And it's 1.2 meters off the ground. So from here to here is 1.2 meters. Okay, the box is 500 newtons. How much work was done against gravity to get to the top? You don't have to actually do think which one do you think? Which equation would we use? A, B, C, or D? Okay, the answers are kind of, the math is correct. Okay, so it's just which equation is the correct one. All right. A couple A's, a B. All right. All right. Everybody's a little shy with this one, and I don't blame you, because we got an angle. It's like, do I use the angle? Do I don't use the angle? What do I do? What do I do? Because it is confusing, right? So it's either A or B. All right, you guys are right about that. So did I say the math is right? Because it sure looks like, I don't know. The point is, here's the deal. It says the work was done against gravity. Oh, somebody's asking me a question. Oh, that's somebody in a different class. All right, so the key here, it says it's done against gravity. All right, right there is your clue, all right? Gravity pulls up and down. Gravity pulls downward. So gravity is pulling downward. The force of gravity is basically this. This is your Fg. This is your force of gravity. So you have to, you're fighting against gravity here. So when we ask what's the work done against gravity, then basically you have to get this 500 Newton box up the ramp, okay? So the Fg is pulling down. You want to get it up to the top. And so, is it glitching? I could restart this. So if it is, so it's going to be this up and down. It's parallel. So because, let me double check my math here. I said it's correct, but I just want to double check. 500 times 1.2 cosine of 0. Yeah. So this is, all right, I won't restart it unless I have more people. Yeah, okay. So that's the key. All right, so the key to this question is, it says against gravity. Gravity pulls downward, and the 500 Newton here is talking about the weight. All right, that's the weight of the box. It's a description of the box. All right, we're gonna have another one, and we're gonna have the other kind in a little bit about when you actually use the angle. But it says the key here is it's done against gravity. All right, that's what you gotta look out for. If it's done against gravity, you're just lifting straight up and down. That's when the angle is 0. All right, I'm not sure if I explained it very well, but that's the explanation I could give you at this point. All right, so maybe seeing the other kind will help. So it could be, yeah. All right, so Maddie, who weighs 400 newtons, sometimes regrets buying a real lawnmower. They're called real lawnmowers, that kind in the picture, by the way. She has to apply 700 newtons of force at a 60-degree angle in order to cut a 13-meter length of grass. So how much work is this for her? So choose carefully. First, maybe decide on what angle, if the angle, and then what are the other numbers going to be? I should have wrote this earlier. I'll write this on the board tomorrow in class. Work is equal to force times displacement times the cosine of the angle. So the equations are basically correct. It's just, did I plug in the right numbers? And the math is correct if you choose the right equation. Okay, good, good. Wonderful. Yeah, you guys are all correct. It is D. So basically when an object's moving vertically, you don't use the angle, but when okay, I'll answer that in a second, Noel. The answer is D. It is D. And why? Because, yes, here's the direction of her force. This is the force. It's going at this angle. It is at the angle, okay? But what's the direction of displacement? Well, displacement is horizontal. And so basically you have to take into account that angle that's right there. So you don't worry about her weight because that has nothing to do with anything. That's just thrown in there for extra. So that automatically gets rid of A and C, all right? And since she is not pushing parallel, she's not applying a force parallel to the displacement. So now you have to use that angle, all right? Does that help? When we go back to the other one, there is no angle between the lifting of the box up and gravity pulling down. They're the same, okay? They're the same, like in the same plane. So the angle technically here is actually 0, which is why A is the correct answer, because there is no angle between, like they're parallel to each other. I know it looks like they're like, it should be 180, but just think of it in terms of parallel right now, all right? Because, well, I don't want to get into why. It has to do with a normal force, but that's the difference between the two, all right? And if you totally just freak out about this, give me a call over during the test and I could try to maybe point you in the right direction, all right? Does that make sense? Like this one is very clearly, she's not pushing in the same direction as the displacement, right? I mean, it's very, very clear. She is pushing at an angle. The lawnmower is moving in a direction that's not at the same angle as she's pushing, right? It's very clear. The other one, maybe it's not as clear, but I mean, then maybe don't use the angle because, you know, this is kind of meant to make you think about it a little bit more. All right, but this is very clearly at an angle. She's very clearly not pushing in the same direction. Okay, I can come back to that if we need to. So ask a question. If you got something to type up, please do. All right. Alrighty. Which of these is not considered work? So only one of these is going to be the answer, not work. And you'll get it right away as soon as you see it. I got a D, another D. Letter D seems to be the popular answer. And you would be correct. D is the correct answer, yeah. Why? Because it is, for the car, it is still moving. It's still moving. The wind is blowing a beach ball. The ball is moving. It's pushing it, and there's a movement. Now, the brake is negative work because the brakes are pushing in the opposite direction. It is D. Good. You guys are amazing. The wind is blowing it. That's pushing it, and it's moving. You carrying your backpack up the stairs, you're applying a force, and you are moving that backpack. But if you just hold your phone in your hand, you're not moving it. You're literally just holding it. Zero displacement. So remember, work is force times displacement. Well, if the displacement is 0, then that makes, you know, it doesn't matter what the force is, this is going to be 0. Okay. So because you're not moving, everything else is moving. If there's a movement and there's a force, there is work being done. Period. Okay. If there's no movement, no force. I'm sorry, there's no work being done. Bink. All right. Unit 4, that is not the whole unit. I apologize. What the heck? I have a lot more questions, as you can see. I'm not sure why it jumped to the end. Let me just start that over. There we go. Are there any questions about the 5.2? Period. Thank you. Yes, to reiterate what Mr. Jern said. All right, let me get to, let's change the color back to purple, blue. All right. I'm glad you guys are listening. All right. So let's look at 5.2. What can be changed in order to directly affect the kinetic energy? All right, kinetic energy of an object. Okay, it might be more than one answer once again. Waiting because of the delay. Gonna drink water because I'm thirsty. A and D. A and D, A and D. All right. Well, kinetic energy is equal to 1/2 mv squared. So what is the m? What is the v? So it is mass and it is velocity. Yep. C, kinetic. Okay, so directly affect it. So yes, I mean, you could store energy and release it for spring constant, but we're talking directly. All right, so it is only mass and velocity can affect the kinetic energy, because those are the two things in the equation. All right, don't overthink it. Maybe you did, maybe you didn't. I mean, you guys all did great. Yeah, and then, yeah, just directly. So good, awesome. All right, oh, I was gonna try something different this time. Oh, well, whatever. What can be changed in order to directly affect the gravitational potential energy of an object? So I'm gonna write this out. Think in terms of the equation. A and D, A and B, A and B. Oh, no L is for the last one. A and B, A and B, A and B. M, G, H. It looks like we got our answer. So once again, mass, gravity, which again, you fly to another planet. All right, I'll award you that one. Okay, no problem, Aiden. And yeah, A and B again. So very good, because that's mass and height. All right, you can't really change gravity. I mean, I don't think. If you can, let me know. I have ideas. Great. Okay, now, a car triples its speed from 10 miles an hour to 30 miles an hour. What happens to its kinetic energy? E squared. E. E. Couple E's. All right. E. All right. Well, mostly you guys are saying E. So here's the deal. Oh, wait. Okay. Oh. All right. Couple A's. Good. All right. Mostly. So here's the deal. We are tripling the speed. So, I crossed it out. I didn't mean to cross it out. I meant to underline it. Tripling, going from 10 to 30. So velocity or speed is squared. So yeah. So if you square it, that means you're going to get an exponential growth. All right. When you triple something, let me just fix that. When you triple something, that's 3 times the velocity in this case. And if you triple 3, you're going to get 9 times the energy. Okay. And you could try this for yourself. So if you're not sure tomorrow or whenever you take the test, plug in just a number for mass. Plug in 10 or whatever you want. Plug in 1. It doesn't really matter. Plug in 2. That way, if you plug in 2 for mass, then it cancels out. And then you're going to find out that if you plug in these numbers, the kinetic energy is actually going to be 9 times greater than what it was if you triple it. Okay. Now, if you double the speed, then you'll have 4 times the kinetic energy. If you quadruple the speed, where you have 4 times the speed, you're going to have 16 times the energy. So it's going to be that square is going to have so it's exponentially more energy if you change the speed. Okay, and it's going to be exponentially less too. I could ask the question a different way, but I just, like I said, try plugging in some numbers, and is that okay? So that's that. So just because of that square, we have an exponential effect on the kinetic energy when you change the speed. All right. So E and B, yeah, B. So you guys who are choosing B or wanted to choose B, that's the reason. Because if you change the mass, if you triple the mass, now you're going to have 3 times what it was, because there's no square. It's not exponential growth. And to get 1/9 of what it was, it would have to be what do you call it? A fraction. Like, we will deal with those later, but it's definitely the square. All right. This one takes a little while to digest. Car of mass m and truck of mass 2m. So it has twice the mass. Driving next to each other at 50 miles an hour. What can be said about the kinetic energy of each vehicle? Now we're changing the mass. Don't be shy. I'm still looking for a way that we can reply without this, but I don't think that's going to be a thing. Let's see. What happens if I throw this up? Nah. Oh well. All right. Good. We got a few. So, yeah. Okay. So now we're talking about the mass. Ooh, there's the mass. Okay. We're talking about the mass. And so there is no square to it. It's just the half. I mean, who cares about the half? It doesn't really matter. That's just algebraic growth. That's not exponential growth. And so if we have twice the mass, you're going to have twice the energy. That's all there is to it. All right. Twice the mass, because this thing has, the car has m and the truck has twice the mass, 2m. You're going to have twice the kinetic energy. All right. It doesn't get squared. It's okay. That's what mess up now, don't mess up tomorrow. Right. So do you understand though, everybody? So twice the mass, it's not being squared like the velocity. So just look for that. All right. You notice, by the way, how I'm always throwing up these equations. I highly recommend that you do that as well. You look at the equations to help like figure this stuff out, because that equation, it's a mathematical thing, but it also it's the relationship between all these variables. So when we talk about doubling things or tripling them or whatever, it's like, look at the equation. See, what does it tell you? All right. Don't try to just like think about it. Look at the equation, and like the equation is telling a story. And in this case, the mass is not squared. So whatever you do to the mass, that's going to affect the kinetic energy directly. All right. Yeah, very good. It's half. So, I see. Well, if you have half the mass, the car is going to have half the mass of the. Ignore the half when you're thinking about these types of hypothetical things. Once again, when in doubt, too, just plug in numbers. I mean, that'll take a little bit more time, so you don't want to necessarily do that. But plug in some numbers you make up, and see what happens if you're not sure. All right, this one might be a little easier if you're familiar with this. Which of these springs is going to be the most difficult to stretch? By the way, sorry if my voice is a little scratchy. I went and did a bunch of bowling with the bowling team afterwards, and there was some yelling and screaming involved, and I may have overdone it with that, but whatever. B. What is that fancy B, Sam? I don't know if I'm what. All right. B. Yeah. Why B? The most difficult to stretch. Well, yeah, that's it. It's a little confusing because at first I'm like, why am I saying B? But it's definitely not B, string B. Yeah, the answer is choice B, meaning spring A, because it has the highest slope. That's it. That's it. Slope is slope for a. It takes more force to stretch it the same distance. So that's it. The higher the slope, the harder it is to stretch a spring. Nice job, everybody. Which one of these has the higher K value? A or B, and why? probably annoying, sorry. Ariadna says B, B. Very good. Same exact reasoning. Because the slope is the K value. The slope is the K value. All right. When you have a force versus displacement graph, slope is equal to the K value. Okay. That is the spring constant for our springs. Nice job, everybody. It is B. All righty. How much energy does it take to stretch this spring 2.2 meters? No. How in the world do I figure that out? Well, let's see what we've got. I need to refigure it out while you do it. Oh, no, I don't. C? A? C? A? Whoa, C or A? C or A? B? Sam, what do you fancy? All right. All right. Energy of a bunch of C's. All right. Energy of a force versus displacement graph. You know, it says X, but you know, meters is displacement. So to find the energy, you had to find the area under the line, okay? Or at least that's one possible, probably the best way to do it. So we got to find the area of this triangle right here, including that little part, all that, okay? And area of a triangle is 1/2 base times height. 1/2 base times height. So half of 0.2. So the height is, so 1/2 the base, so 0.2 times the height, and the height is going to be 6 newtons. And so 0.1 times 6 is going to be 0. Hang on, 0. I think that's right, but you know what? It's always good to double check. Yeah, all right, thought that was too easy. All right, 0.6. I put this together on Saturday, by the way, when I thought we were going to do this on Sunday. No, I did it on Thursday or Friday. So the answer is going to be 0.6. So Sam and Ariana are correct, and perhaps Stephanie, I think, and maybe somebody else that I can't see up there anymore. All right. So you guys were saying C. I'm not sure why. Maybe because you just went over and up. That is equal to, letter C is equal to how much force it would require to stretch the spring. Because you read the graph. You read the graph. This tells you, all right, it takes 6 newtons of force to stretch the spring to 0.2 meters, all right? But to find the energy, you have to find the area under the line, all right? All right. Moving on. Let me know if you have questions. With the delay, it's okay. I'll go back. What's the K value of this spring? Remember I told you earlier. Well, K value. I had to cough. K value, I said it earlier, is the spring constant. And when you have a graph of force versus displacement graph, you have to find the slope. And slope is, if you want to get the whole equation, y2 minus y1 over x2 minus x1. We're getting lots of D's. Wonderful. Let's see. Now, I highly recommend using 0, 0 as one of the points. Always. If it goes through 0, 0, use that. It just makes this whole equation a whole lot easier. I'm also going to use this one. So this will be 0.2 comma 6 will be my x2 and my y2. So basically I could just take 6, and I suppose I should stick with the units, divided by 0.2 meters. That's going to give me, well, you guys are all saying D, so I'm thinking that's right, but I just like to double check my work here. Yeah, you guys are fantastic there. That is going to be D. So that'll give me 30 newtons per meter for my spring constant, okay, for my K value. Nice, good, very good. And like I said, okay, little pro tip, use 0, 0. If it looks like it goes through 0, 0, it probably does. You could assume it is. So that'll make the calculation a little bit easier. What is the K value of this spring? This spring right here. Wait a minute. Oh, we did that one. I don't know what I was thinking. All right, a spring that is stretched stretch D stores X energy. How much energy is stored if the spring is stretched to D? What? What am I asking? Okay, basically, bottom line is it's asking if you stretch it twice as far, how much energy is going to be in that spring? Hesitations. B, good. I'm not saying it's right, but good. We got answers. B, question mark. That's not an answer. All right. So we want potential energy of elastic. It's 1/2 times KD squared. We got, all right, good. It looks like we're between B and D. All right. Well, we just doubled the displacement, right? So if we double the displacement, all right, what are we doing to the displacement? We are squaring it. Remember this from before? Yeah. All right. Remember, so if we double it and we're squaring that doubleness, that means it's going to give us quadruple the energy. It's going to give us exponentially more energy. So if it was 3D, 3 times the distance, then that would give us 9 times the energy, okay? If it was 4 times the distance, that would give us 16 times the energy, okay? If it was 1/2 the distance, that would give us 1/4 the energy, all right? I'm not saying I'm gonna like that, but that's how it goes. So if we have 1/4 the distance, we're gonna get that's gonna give us 1/16 the energy. All right, you see how that goes, especially the the top ones. So you square because look at the equation again. So always go back to this equation. You got the equation saying square the displacement. All right, don't do anything to the K value. So if you double the K value, it's just gonna have double the energy. There's no squaring involved there at all. Okay. All right. Fun stuff, right? All right. Let's see. I think that might be the last. Oh, no. Okay. Yeah. So that's it for the types of energy and all those equations. All right. You can see what we're getting into now, but that's it for the equations. So if we have questions, let me know. We can come back to those. If we're unsure, can we pick the random number for K? Absolutely, you can. Yes. Noel, that is a phenomenal idea. With any of these equations, if I'm just giving you like hypothetical situations, absolutely pick a K value, pick a number, make it 2 again, okay? If you make K value 2, then you're just gonna have to, and that's 1/2 of 2 is 1, you just multiply by 1. Yeah, pick a number, absolutely, okay? Good strategy for all these equations, that'll work. Okay. All right, graphs, energy graphs. Energy graphs. A kid sleds down a frictionless hill. There used to be this thing called snow. It happened during the winter, and it made hills really slippery. It was really fun. You may have heard of it. I don't know. And so he's at the top of a hill, and he's sliding down a hill. Which of the following graphs represents the energy of the kid who's at the top? All right. So I'm seeing A. Yeah, the answer is A. Not too tough because he's at the top, right? Top of the hill. So here's the kid right here. He's that blob, and yeah, so he just has potential energy, gravitational potential energy, nothing more. He hasn't started moving yet. All right, so here's the deal. Potential energy is all about if there's some height involved. If he's up off the ground, so I guess I would call this, I'm gonna screw this up, but this is gonna be the 0 height. Where do we go? There we go. Lost my pen for a second. So this is 0 height, and if there's a height from that 0, they're gonna have potential. So the objects will have potential energy. If it's moving, okay, then it's gonna have potential kinetic energy. Sorry. If there is a spring involved, just to kind of get this down to bare bones, if there's a spring involved, it's gonna have elastic potential energy. So since he's not moving, there's no springs involved, the answer is going to be A. It's all potential energy. You notice the total is, just like the energy skate park thing. All right, kid slides down a frictionless hill. Which of the following graphs represents the energy of the kid when he is at the bottom? So we're going to assume this kid is at the bottom. Here he is on his hill again. He went down, and now he's at the bottom of the hill. He's just kind of came down from the top of the hill. Don't overthink this one, right? Yeah, exactly. Don't let my poorly wording, ambiguity of my questions throw you off. The kid's moving at the bottom of the hill. There is no height. So no height means no potential gravity. There's no springs. It's all kinetic. All right. All right. Good. So the kid floods down a frictionless hill. Which of the following graphs represents the energy of the kid when he's more than halfway down the hill? All right, see how I'm drawing too? I mean, it might help you to draw it, I don't know. The kid is roughly, well, no, more than halfway. So let's just get rid of that. And the kid is more than halfway down the hill, moving down the hill. B, 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 B. All right, I would say that seems about reasonable. Yes. Q, let's see. Definitely not that one. Definitely not that one because there's still, so it's not A because the kid has kinetic energy. It's not D because he has, the kid has some potential energy. And then now it's a toss up between these other three, I guess. It's not C because that would be halfway down the hill. So that's halfway. Halfway. That's handwriting for you. It's probably not E because it looks like he's not, like he's higher up, like E might be like up here. Like he's just barely starting to move. He's got some kinetic energy, but mostly he still has potential energy, right? So the answer is B. Nice job. You guys are good. They're just fancy people, Mia. I don't know. All right. I think this is the last kid down the hill question. Kid slides down the hill. There's some friction, but she has fun and is going pretty fast at the bottom. Which of the following graphs best represents the energy of the kid? Do. Fancy people drink fancy water. That's not it. All right. Little more thought in this one. That's okay. So these graphs have work involved, right? External work. That's what this WX means, right? There's some work being done. And work either, holy cow, adds or removes energy from from the system. Okay. So in this case, there is friction. There is some friction. It's friction add or remove. Well, friction removes energy. It's a negative. All right. It takes away energy. So it looks like we're between B and D here. So we're not saying A, which is good because it's definitely not A. Why? Because here we have work adding energy to it. And even if we were to add it, we go up to 10 here. These things should add up to 10 plus 2 more. This doesn't even make sense at all. It has to add up to the 10 plus the 2. Nobody's saying C, which is also good because once again, we have our positive work. And we have 10 kinetic and we're adding 2 more. So we should have 10 plus 2. Even if it was adding energy, this doesn't make sense because it has to add, I don't think anyway. 1, 2, 3, yeah. So it doesn't make sense. These two are both possibilities because these are both negative energy. They're removing energy from the system, from the kid. All right, so these are both good in that regard. Okay, it could be B or D, right? So the question is, what is the kid's initial energy where he started at, or she started at? Well, she started down, or she started at the top of the hill. So she started at the top of the hill, and basically, since she started at the top of the hill, yeah, it's got to be D. So she started with some potential energy. She started with, if you count the lines, there's 10 lines. Friction, I had to take away 2 lines of energy. So in the end, she's still going pretty fast at the bottom of the hill, but she doesn't, did I take away 3? It doesn't, I don't know. Maybe it only has 5. So it has 5 lines, I apologize. So 5 lines. So I took away 2 lines of energy. So she only has 3 lines of energy left. It's kinetic, she is moving. Okay? But that's the story that these graphs are telling us. This kid here starts with kinetic energy. There's still some friction taking it away. And in this case, the kid still has some kinetic energy, but has also climbed up a hill. But this one doesn't make sense because we have 5 lines of energy. Now, I'm not saying this is going to be the case, but I'll answer that question, Giselle, in a second. It's a good one. But this one doesn't even make sense because we take away 2 bars of energy. So like this should like total up to, these 2 should equal what, 3? And they don't. Okay, so this one doesn't make sense because it doesn't, like the math doesn't work out with how it's represented. Is it negative because she's moving down? No, it's negative because the friction is removing energy from the system. She has a certain amount of energy and it's getting taken away by the friction. Does that make sense? Now, if she was sitting there doing the thing with her arm and pushing herself, that would be positive energy because now she's adding energy by pushing herself a little bit along the way. All right, so that's the difference between positive and negative energy. Positive energy is adding energy to the system, and negative energy is taking it away. It has nothing to do with what direction they're moving or anything like that. Okay? All right, so I hope that makes sense. Now, these all had, except for D, they all had like a poison pill to them. Oh, I'm sorry, Mia. I might be recapping here, but these all have a poison pill because if you do the math, they don't add up. All right, no matter what, for A, B, and C, they don't add up. Like I said, this one starts with 5, and we're adding 2 more, so these 2 should equal to 5, 6, 7, and I don't think they do. They don't. Okay, so right there, that tells you that's going to be wrong. I'm not saying this is going to happen on the test, but I'm just telling you, like, these are kind of weird examples and bad examples, but that's how the work should work. Is this one starts with 5, we're losing 2 because of friction, so I guess I'll put a negative 2, and we're going to end up with 3 bars of energy. Okay, so that's how work does. Work is positive if it adds energy, like somebody pushing her, like there's the wind pushing her, or her brother comes up from behind her and decides to push her into a tree or something. Like that's adding energy into it. Okay, but in this case, there's friction, and that's taking away the energy. All right. These graphs are also a little, what do you call it? Not 100% accurate, I think, to say, because the work doesn't happen at the beginning. The work is sort of happening in the middle. So honestly, I feel like the work part should be separate from the beginning. So in the beginning, she was not moving. There were no springs, but she was sitting on top of a hill, and she had potential energy. As she started going down the hill, there was some work done. It was negative work because of friction. It took away. And then at the end, she just had kinetic energy. Okay? So what is the story of these graphs? That's what you got to ask yourself. Sometimes the story might not make sense and might not add up. Okay? But I don't think they're all going to be like that. I think they're just going to be different options of graphs that actually do tell an accurate story. But you have to just make sure it's telling the right story. So the story for this one, the kid has potential energy. She loses some energy due to whatever. In this case, it's friction. And so she ends moving, but not with as much energy as before. All right. All right. A couple more, I think. We're almost done. All right. The kid has the hill, 5,300 joules of PE and 700 joules of kinetic energy. What's the kid's total mechanical energy? Actually, I know we're not done because there's one thing that you guys all want and we haven't gotten there yet, but it's coming up. Hope your internet doesn't drop out for that part. But I guess I know you're here, so. All right. Kid's total mechanical energy. I made this kind of an easy one. Yeah, so total mechanical energy is literally just kinetic energy plus potential energy. All right. So here's your potential energy. Here's your kinetic energy. Add them together. What do you get? Yeah, you get C. Great. All right. Nothing too hard about that one, but it's definitely worth mentioning. All right. You'll see sometimes there's just extra numbers like, what is this for? What is this for? Don't worry about it. Okay. It doesn't matter. Sometimes I give you the answers in the problem. Okay. Wink. Same story. That last one was the kid's total mechanical energy at the start, or where they were. What is the kid's? So the kid starts out on a 10-meter hill. Now halfway down, what is the kid's total mechanical energy? All right, if you remember from before, it was C. It was 6,000 last time. So what is it going to be halfway down? All right, seen a bunch of C's already. Yeah, you guys are good. All right. So that's the thing. It doesn't change. All right. So if you think of anything else, doesn't change. Okay. I guess I'll say unless there's work happening. Okay. Work might take or add some or take some out, but yeah, it's not going to change. All right. If I just ask a straight up question like that, it doesn't change. Great. All right. At the bottom of the hill. Thank you, Lexi. I appreciate that. I'm writing on a little thing that's horrible to write on, but I'm just kidding. Actually, I'm not kidding. That's what I'm writing on. I have horrible handwriting anyway. All right. That is no secret, but thank you. I appreciate the input, feedback, whatever you want to call it. C, I'm getting C again. Yeah, all right. Yeah, I can't fool you guys. That's good. The TME doesn't change. It doesn't matter where they're at. It's going to be the same thing. So, I mean, keep that in mind, because if you see like a roller coaster of like all this stuff happening, you know, it's like once there's a question on some of the practices, there's a question on the review guide. Once you find the total mechanical energy anywhere, the total mechanical energy is going to be the same everywhere. And so, like with one of the practices, there was a question where it's like, all right, well, if I know the PE for one of these places, I could just subtract and I could figure out the kinetic energy plus kinetic energy. All right. So that's just going to be the same. It's always going to be the same everywhere. Even here, not there, here, anywhere on the track, it's going to be the same. All right. That's not the question, but yeah, I mean, it could apply to anything. Okay. Kid is, now this is a real question. What's the kid's speed at the bottom of the hill? All right, bottom of the hill. So take some math. I'll start talking because, you know, so you guys got a calculator. So there's only one equation really that deals with speed, mv squared. So there's your velocity. So what kinetic energy does this kid have? Well, he's at the bottom of the hill suddenly. There's the kid. Okay. So we already know the total mechanical energy is, what do we say, 6,000? Yeah, right, well, 6,000. Okay, joules. We want to know, well, we want to know velocity, right? But to know velocity, we know the kid's mass. We need to know this kinetic energy. Well, we know that this is equal to the PE plus the KE. And if he's at the bottom of the hill, that means that potential energy is going to be 0, which means that the kinetic energy is going to be 6,000 again. All right. So he's at the bottom of the hill. It's all potential kinetic energy. And so, good. I haven't decided yet. I'm still working through it. I think I know what it is. So I think I know what happened. You guys forgot to square root it. Okay. So kinetic energy. Well, you know what? Let's just write the answers in. So the kinetic energy is 6,000 joules equals 1/2 the mass. So it's 54 kg. And we want to solve for velocity. Well, 6,000 joules is equal to half of 54. So is that 25, 26, 27 kilograms times velocity squared. If I divide both sides by 6,000, or 6,000 by 27, so I'm divided by 27, divided by 27. I'm guessing, I think that gives me 1,9. Holy cow. Lexi, you messed me up because my handwriting was great until you said something. Just kidding. All right. I'm thinking, double checking my work though, because I don't want to like assume anything. So 6,000, I'm pretty sure you guys all are like waiting. Yeah, we know this, Mr. Jern. But 6,000 divided by 27, yeah, 222, 222, 22, 22. Okay, wait. Why do you add the together when all you need is the kinetic energy? All right. Noel, I will answer that question in 1 second. So when I take 6,000 divided by 222, 22, 22, I get, that's the answer I get when I divide that. And so that's my velocity squared. Yes, Aiden got it. So, right. So when I take the square, why do I have two of these? That's nothing. All right. So velocity squared, I take the square root of that. I take the square root of that. I believe my answer is D. Most of you said it was, and it is D. All right. So that is the answer, D. Nice job, everybody. Right. Aiden is correct. So how do I say this? So at the beginning, the kid has a certain amount of potential energy and a certain amount of kinetic energy. That tells me the kid is not at the top anymore. The kid has actually already started moving. Right, so we already have a combo. You just add them up, but at the bottom of the hill, the kid has 0 height. So right, it's all, the total energy is 6,000. All right, I did throw these in there because I believe those answers are if you base it only on one of the two. I forgot, like 5,300. And you did everything correctly, but with the wrong number, you would get those answers. But that's how you get it, all right? So the kinetic energy is all you got at the bottom. It's the total, and then you just plug it into this equation and solve for velocity. Yes, thank you, Aiden. You were correct. All right, for some extra credit, what was the last thing you ate that was yellow? Set a timer for 30 seconds.
Setting.
Thanks.
Your timer is set for 30 seconds.
You're so fast, Siri. Mac and cheese. Oh, yummy. Banana cheese. Oh, wow. These are good answers. I wasn't expecting these. Nice. All right, I'll give you eggs. Gummy bear. Nice. All right. I'm with you on the eggs. I just had egg as well. Nice. Tortilla. All right, yeah, I guess it's yellow. Nice, nice. Yeah. Wow, a lot of eggs. Very cool. All right. Now I want pineapple too, by the way. Lemon candy cane. Wow, really? Is that any good? Wait a minute, Becca. You said tortilla. Did you eat those together? Like now I'm picturing a lemon candy cane wrapped in a tortilla. Oh, you guys are getting gross. All right. I'll take it, Mia. That's fine. Yes. All right. All right. Which ramp? Gramp is different. Which ramp is going to give the ball the greatest speed at the bottom? A, B, C, or they're all the same? I'll still take answers to the yellow question, by the way. Thank you, Tess. All right, good. So yeah, I mean, it's all the same. You guys can't trick you because it has a certain amount of, hello, F. I don't know why I wrote you. You know what? I was going to write potential energy here plus KE is going to, this is our total mechanical energy. And we did this in class. Yeah, it's D for sure. And we did whatever it has potential energy is going to be X. It's going to have 0 kinetic energy. And all that potential energy is going to be the TME here is going to be the same total mechanical energy. But now the PEG is going to be 0, which means that it's all going to be kinetic energy. All right. Be able to explain that. All right. It's all kinetic energy. So kinetic energy is going to be equal to X. Whatever potential energy it had at the top, it's now going to have that kinetic energy at the bottom. All right. You guys all got that. All right. Just make sure you know why. Make sure you know why. All the potential energy that it had at the top is now kinetic energy at the bottom. All right. So, I am very proud of my drawing here. So I drew this, and I just want to take a minute and appreciate my drawing skills when I feel like when I take the time to actually draw. For real though, what is the minimum distance required to push the 12 kilogram ball with 175 newtons of force so that it rolls up to the top? And this is the last one. Yeah, this is the last one. Thank you, Lexi. I very much appreciate that. So that we're going to assume no friction, okay? But how much distance is required to push this 12 kilogram ball, up to the top of the hill? Okay, how much force? What is the minimum distance? Yeah, I actually looked on the internet and I couldn't find a drawing of what I wanted. So, yeah. So, you might not even know where to start this question. Okay. You might not know where to start. We want to know, what is the minimum distance? All right. So we want to know a distance. I think there's only one equation that deals with distance or displacement, and that's going to be the work equation. I mean, I guess the spring equation would work, but it wouldn't work because there's no springs. And height, that's not it either. That's height. That's not distance. I try. You got these compliments don't affect your grade much. So anyway, the only equation that really deals with a distance or displacement is this one. All the other ones, yeah, okay. So, but be ready. This is the last one. So I'm gonna spend a minute or two on this one, and then we'll be done. Okay. So hang on to your brain for a minute. My brain's going too. It's late, and I'm tired. And we all had eggs. So yeah. Now, so, and it's kind of nice because it tells you we're going to push it with a certain amount of force. So we know force. We need to know the displacement. Thank you. We need to know the displacement. Okay. We know the force. It's 175. What's the work done? Well, this one kind of, how do you know what work is done? Well, remember, work is equal to how much energy that the ball is going to gain. How can you figure out how much energy the ball is going to gain? Well, we know it's going to be up here and it's going to gain some PEG. You start to think about how to do this now? Okay. Well, PEG is equal to mass, gravity, height. We know the height, we know the mass, we know gravity is 9.8. We can figure out how much work needs to be done because we can figure out how much energy this ball is going to have when it gets to the top of the hill. So let's figure this out. So PEG is equal to the mass, 12 kilograms, times gravity, 9.8 meters per second squared, times the height, which is 2.2 meters. And so Ariadne says A. I don't recall. I don't know. 12 times 9.8 times 2.2. I got 258.72. 258.72 joules. Mr. Jones, should I round? Should I round? Should I round? I wouldn't until the end. Okay? Don't round until the end. Don't round until the end. Okay? So that's how much PEG. And so that means that the work is equal to the work that needs to be done. 258.72 joules of work needs to be done. So that means we got two of the three numbers. We got this. This is good. Okay. All right. So I'm going to pre-rearrange this. To solve for work, I'm going to have to divide both sides times, divide both sides by force. So work is force. Got a couple A's. All right. Work divided by force. That's a horrible. All right. Eraser. Let's erase that. While you guys are figuring this out, I'm just going to. Oh, dang it. P. So work divided by force is going to give me my displacement. All right, so displacement is going to go, so that's going to be down here now. So the work done is 258.72 joules. Got a big number. Let's see what happens here. The force is 170 A's for Aiden. You're right. Cool. All right, so divide 175. I divide that. And I got the answer is 1.4784 meters. So 1.784, that does round to A. And, well, yeah, but you go by Lexi, so I don't know if that counts. But it is true. It is true. The answer is A. So you guys got it. A and D. Why D? Why D? Where does the 6.6 come from? I don't know where that came from. And all right, you guys, it's definitely getting late. You guys are getting goofy. Man, all right. So yeah, that's how you do it though. So to recap what I just did, it's like, all right, we want to know the distance required. So there's only one equation that does distance, and that's going to be this equation right here. So we have to solve for distance, and we know the force, but we don't know the work. How much work is going to be done? Well, how much energy is the ball going to gain when it gets to the top of the hill? Okay, and this goes backwards too. So like maybe the ball is on the top of the hill, and it's going to be negative work. All right, maybe somebody needs to slow the ball down. Okay, it's the same idea. How much work needs to be done? And so then how do you solve for it? Physics is an amazing subject, and it really does, like, it's crazy sometimes when you got a test tomorrow too, so there's part of that, a little bit of stress maybe. All right, any questions? A and B. Any questions on that last question or anything in general? All right. Well, we're just a little over an hour. I wish we could do this all day. I know somebody suggests I should stream Minecraft or something, but yeah, I don't know. I don't think I'm going to right now. I have a question. Oh, right. Thank you. All right, number 5 on the review. Yeah, let me switch to that really quick. Whoop. All right. I say that occasionally. Bink. I do say weird things. Oh, okay. No note card. No note card. Oh, I hope you will pass. Will I pass thanks to this? I hope so, Becca. I mean, I hope it was useful. I don't know. Hope so. Good luck. All right, number 5. What's your question? Number 5 on the review. It says, walked up. Oh, you may have missed that other question. I'm going to summarize, and then I'm going to say rewind this. Rewind and go back to like one of the beginning questions. And the key here is, again, it's doing against gravity. All right. And since gravity is basically, you got to push. So you're going to push down. The stairs are going to push you up. And so the stairs are going to push you up. So that means the force is going to be directed upward. And because we're worried about gravity, the displacement is also going to be upward. And so since they're in the same direction, that means that the angle between them is going to be 0. And so you can do force, the work is equal to force times the distance times the cosine of the angle. And the angle is going to be 0, which makes this equal to be 1. So you just basically, how do you know to use? Because this 7 meters is going to be vertical. That's going to be the up and down displacement. That's actually Here's what I think. Here's what I say. When you push on the stairs, you're pushing down. The stairs pushes you up. The stairs doesn't push you from side to side. At least not, we're not dealing with that aspect of this. We're dealing with the students. Hello. We're dealing with the student's weight, which is the force of gravity down. And so, yeah, that's how we do it. So we're dealing with the force being pushed upward to push you up the stairs, and so there is no angle between them. Now compare that to this one where you definitely have the dog is going in one direction and the force is going in the opposite or in a different direction, not like parallel to it. So this one you would have to use this this angle for question number 6. For question number 5, you could just ignore that angle. All right. Yeah, I agree. Becca, you're going to do fine. Again, just rest and you'll get it. All right. The dog question. Yeah, my dog did that. My dog did it, does it too. Dogs are fun. So I don't know if that answers your question. All right. What do we got? Number 19, really quick. I'll go through it kind of quickly. So 19. Oh, okay. Which part? All of it? Part D. Okay. So 19, part D. And then I'll do number 26. Speed of a car when it is 5 meters from the bottom. Good question. Good one. So you have to know, I don't have the key in front of me. You have to know, once you get the TME, you're going to get some number here. I forgot what it was. All right. I assume you got that. Do you have it? You can type it in. I'll adjust. All right. So you need to know that one. And this one actually, I kind of did one similar to this when the kid was partway down the hill. I think I did this one. So to do part E, 20. Okay, good. I thought it was something. I knew it was 29,400 joules. So that's the total mechanical energy. And the thing is, you need to know the kinetic energy so that you could solve for velocity, right? And that's where you're running into problems. Well, what is the kinetic energy? Well, the kinetic energy is going to be equal to that 29,400 minus the potential energy of gravity. So you had to solve for the potential energy of gravity here by taking the 5 meters, multiplying it by the car's mass, and 9.8, and then you subtract it. And once you do that, you can solve for the velocity. All right. So you'll know what the kinetic energy is when you subtract it. Okay. Lexi, none taken. If you can see my setup right now, I'm kind of like, it's almost like I'm doing physics twister right now. All right, here's my hand, here's my face, and they don't line up how they should right now. So, but yeah, that's why. And here's my microphone. So does that help, Noel? Does that help? So I don't, let's see the numbers here. Let's see if that helps anyway. So 9.8 times, yeah. All right. Let me know if it doesn't help. I can come back to it. So number 26, and I'll come back. Good. All right, number 26. You know what? 18's right here. I'm going to do 18 really quick, Valeria. So how much energy does it take to compress a spring 1 meter? All right, so for this one, energy, and you have a graph. Whenever you see energy in a graph, you should automatically think area under the line. Okay, so energy is equal to area. Spring constant or slope is, well, the spring constant or K value is the slope. Okay, so to get, yes, good. Tess, I think you might be on a heck of a delay. I'm not sure though, but you are right. So I want to compress it 1 meter. And so I'm literally just going to find the area of this triangle right here. All right, so the area of the triangle is 1/2 the base times the height. So it's going to be 1/2 of 1 meter times the height, which is what, 25 newtons. All right, solve that. That'll get you the amount of energy. All right, Valeria, it's a delay. I'm going to come back to you. All right, Valeria, let me know if that helps. I'm going to just pause there. I can't, well, 1/2 of 1, so 1/2 of 25. So the answer is going to be 12.5 joules of energy, I think. All right, if I might just be doing this a little too quickly, but Yeah. All right. I'm gonna take your silence as you get it, or at least not, at least I haven't heard from you yet. All right, number 26. Awesome. Good. 26, 26. That's on the back. Oh, yeah. All right. 26 is almost exact. It's the inverse of the last question I just did with the ball rolling up the hill. All right. So I think was the force applied? Yes. So it is very similar to that one. So we want to know what the force applied is if we stop it in 0.6 meters. So we want the force. And so for this one, the only equation that uses force and distance is going to be our work equation once again. So we could ignore the angle because we're just going to assume it's 0 degrees. So so in this case, we know the distance, it's going to be 0.6 meters, but we want to know the force. So we're going to have to figure out the work again. And since work is equal to the change of energy, all right, then we need to figure out how much energy was changed. All right, in this case, if we look at this, we have a certain kinetic energy here. All right, so if you figure out the kinetic energy, well, it tells you mass and can we 1/2 mv squared force applied. Hot Wheels in a physics lab, blah, 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 blah. I feel like we're maybe missing something. Hot Wheels and it starts. Oh, okay, holy cow, this is like a multi-part thing. We want to know how much kinetic energy it's going to have here. And since we don't know the velocity, we can figure out how much gravitational potential energy it has here, because all this gravitational potential energy becomes kinetic energy. And then the friction does work to remove that energy. All right. So I'll just work you through it and we'll figure this out. So it's mgh. So I'm going to take the mass, which is, I guess I'll write it down. So 0.07 kilograms times 9.8 times the height, and it tells us 1.5 meters. 1.5 meters. And I apologize on my handwriting. I'm trying to balance out doing this quickly and doing it nicely. So 0.07 times 9.8 times 1.5, I get 1.029. Okay, so it has that much 1.029 joules of potential energy at the top of the hill. All of that gets turned into kinetic energy, okay, because there's no friction yet, not until it goes into the box. So now it has that much kinetic energy, which means if you did this little bar chart thing from B to C, it's going to have, I don't know how much energy. Let's just say it has all kinetic energy and it goes up to the top. All right. That means it's going to lose, well, it's going to come to a stop. And since it's going to come to a stop, it has to take away all the energy. So the work done is going to be equal to the amount of energy that it had, because that box that it runs into is going to take away all the energy. So how much work does the box do? It's going to do 1.029 joules of work, because it has to take away 1.029 joules of kinetic energy. And since it does we could argue, okay, is it negative? Yeah, actually it is negative because it's taking it away. But don't let that part confuse you, all right? I just needed to throw that in there because that's what it is. So now we know the work, we know the distance, and we just have to solve for force. So if we take this equation and we rearrange it to solve for force, force is going to be equal to the work divided by the distance. And now we know the work is negative 0.029 joules, and the distance or displacement is 0.6 meters. And so I get negative 1.029 divided by 0.6. I got my answer. I believe that's what I had on the key is 1.7. I'll just round it now. So negative 1.7 joules. I don't know if I had negative on the key, honestly. Oh, it's not joules because it's supposed to be a force. So it'll be newtons. Okay. So you see how that was related to that last question on the other one. It's the same idea. How much work is being done, whether it be positive or negative, it doesn't really matter. It's just how much work is being done. And to know how much work is being done, you have to know how much energy that it either had or it's going to have. If you're adding energy with the work, like in the example problem from the slideshow, then how much energy is it going to have after you do the work? In this example, how much energy did it lose? How much energy was taken away because of the work? And so you have to figure that out. All right. That is a good question. I'm glad somebody asked that because it's a complicated question, obviously. It's probably one of the hardest questions because it's just, it kind of takes into account everything. Okay. You are very welcome. I had 1.72. Okay. So yeah, because look, that's my answer I got. So I rounded differently. I just rounded to more decimal places on the key. Okay. Good. Any other questions? All right. I will be there first period. I know that doesn't help Lexi. Sorry. But anybody else could definitely come in. Even if you're not my student, I suppose I could help you. I don't mind. But you might want to ask your physics teacher. But yeah. Any other questions? I think I might call it if I don't see any. We're going on an hour and a half. You guys are rock stars at this. If you're still here, nice job sticking with it. It's fun. Well, I have fun. Tired, but it's fun. Yeah. Well, you got fancy handwriting. Tell me how you got. Oh, okay. Noel. See, I'm getting tired. Sorry. Reading your name instead of seeing you. How did I get the negative? Okay. So the work, I got that because up here, it's because this car, okay, so how do I start? I needed the work done. I needed to know how much energy was lost, taken away by the friction. So I needed to know how much kinetic energy this thing had to start with to lose. How much kinetic energy it had, I didn't have the velocity, so I can't figure it out that way. So I had to be like, well, okay, whatever potential energy, let me just fix this because I do have terrible handwriting. So whatever kinetic energy it has down here, that's how much that energy came from the potential energy that it had up here. So if I could figure out the potential energy up here, which I did, 1.029 joules, then that's how much kinetic energy the car had when it hits the box. Why is it negative? Don't let the negative throw you off. But so that's how much energy needs to be taken away, which is why I put the negative, because the matchbox, the box that the car runs into, is going to take away that energy. All right. That's where I got the negative 1.029, because it's just equal to the amount of kinetic energy that it had, and it's taking it away. In that last question, I figured out how much energy it's going to have when it goes up the hill, which is why this is why this stayed positive, because this is how much energy it's going to have after I do the work to push it up the hill. Similar question. Okay, for this one, it has the energy, but now it's going to take it away, which is why it's negative. Awesome. I'm glad you get it. Anything else? I'll stay here all night, but only if we're talking about physics. Yeah, good. Well, let's call it. I thought this would be like a half hour, 45 minutes, but yeah, it's good. I mean, this is good. You guys are, I think you're ready. All right. If you get this, you're gonna be ready for tomorrow's test, I think. All right. So, okay. Second. See, I got to remind, and it was from another class again. Actually, it says my clock tower boosted the variable. Okay, no question. You guys, yeah, you bet. Yep. All right. I am out. I'm going to stop the stream. I'm going to stop the recording. I'm going to stop the stream. You guys have a wonderful evening now. Yeah, no problem. Thank you guys for coming. I will do this because if it helps you guys, I love doing this. This is great. So yeah, no need to thank me. This is good stuff. So thank you guys for coming. And I really hope it helps. And good luck. Study hard. Get some rest. Yeah, you're welcome. You're welcome. All right. Take it easy. Have a good night.